Shall I start now? Hello. Shall I start? Am I audible, Bhaskar?
Yes, sir, you are audible, sir.
Okay. Just check whether PPT is coming or not.
Yes, sir, it is coming.
Now it is. Just a minute. You take that screenshot, okay?
Yes, sir.
Is it coming?
Yes, sir, it is visible, sir.
Okay. Good afternoon. Sorry, good evening to all. Welcome to this BSc. Today, my discussion is on RIS and UAV-assisted communications. My lecture outline is first I'll introduce the RIS and UAV. I'll give a little bit introduction on that. Then I'll talk about RIS-assisted communication. Then UAV-assisted communication. Thereafter, RIS and UAV-assisted communications. First of all, what are the present problems? The present problem is that mobile devices or user applications are increasing rapidly. Due to that, we need a massive connectivity. And as far as the requirement from the user end, and applications, we need high data rate and low latency. So the existing techniques are now at the saturation level. Since we need high data rate, ultra low latency, and massive connectivity, we have to look for some other techniques, modern techniques, advanced and adaptive techniques. So if we look at that limitations for 4G and 5G, 4G LTE and 5G scenarios. Here, if you look at here, 4G and 5G NR performance mainly improved. Till now, whatever the development is going on, and still it is under research, that is from the transmitter side as well as from the receiver side. Whatever the implementation have been still adopted, means either you use multiple antenna for say massive MIMO, antenna at the receiver as well as at the transmitter to combat fading, or to increase data rate, or beamforming. Adaptive and advanced modulations. Adaptive and advanced. These are the existing. Some are existing, some are already proposed. Adaptive and advanced modulations here. Adaptive means basically based on the received conditions. Say if the SINR is bad, then you go for QPSK modulation techniques. If the SNR is medium, dissipation is medium, then go for say 16 com. If dissipation is very good, then go for the 16 com. So this is the one kind of adaptive modulation. Still now, if you look back to the previous modulation techniques in communications, if it is a QPSK, both transmitter and as well as the receiver, both they were same. Whether it is a QPSK means transmitter is QPSK modulations, at receiver is a QPSK demodulations. Or if you look for other modulation techniques, QAM and all, same at the transmitter as well as the receiver. But in case of adaptive, it based on the dissipation and conditions. Similarly, some other advanced modulation techniques are there also. So basically, if you think about a transmitter, TX and RX, whatever the developments done here or here, that in between that the channel nobody touched here. Right now, people work is going on here. Channel. Before implementing this today's topic, the RIS basically channel was not in our control. It was once the RIS is implemented, till research is going on. Some where it is that some small you can say prototypes have been made and tested. So the use of RIS when the use is adopted in the communication system, it is observed that channel is to some extent under control. Okay, so basically whatever the development done still now, that is in the receiver transmitter side as well as in the receiver side, but still the propagation environment remains uncontrolled still now. So how we can control? Why, first of all, why they are uncontrolled? Because severe path loss. First case, severe path loss. Second, blockage. So number of, if there is a buildings, forest areas are there, so obviously there will be a blockage between transmitter and receiver. So it will create a blockage as well as shadowing. Multipath fading effect also there. Multipath fading. Due to multipath fading, that the problem is that there will be delay. Just a minute, Mamta. Due to multipath delay, multipath components, what happened? The same signal is reflected from different objects and reaching to the receiver at different delay. The delay spread is problematic. If the signal period is greater than this delayed RMS delay spread of the channel, then no problem. It's a flat fading only. So there is not too much harmful, flat fading. But if TS is less than RMS delay spread, then it's a frequency selective fading. It is a problematic. Frequency selective fading. So this is the major concept. So somehow you have to take care of the delay of the channel RMS delay spread of the channel. Now, for just a small that RMS delay, it may raise confusion to some listeners. What is a delay spread? Is basically say if you have a transmitter TX and there is a receiver RX, there are multiple reflectors. Say reflector 1, R1, reflector 1, reflector 2, reflector 3. So signal is hitting there, reaching to the receiver. Signal is hitting here, reflector 2, reaching there. Signal is hitting there, reaching to the receiver. And one is direct path, if there is no blockage. So obviously the direct path will take less time, so it is a T low. And any one of them which is the farthest distance, say this R3 is the farthest distance, so it may, this distance is maybe, the delay is maybe T high, highest delay. Through all the paths, same information is traversing. The time difference between these two, tau high minus tau low, is called delay spread of the channel. If this delay spread is greater than the transmitting signal period, then it is a problematic. Then there will be frequency selective fading, means inter-symbol interference will be there. Then you have to use equalizer at the receiver to remove the distortion. Another case is user mobility. If the receiver or there is a relative motion between transmitter and receiver, then Doppler shift will come. And when the Doppler shift comes, there will be fast fading. There may be a slow fading. Okay, that depends on channel coherence time. If the coherence time, say coherence time TC, If the coherence time greater than TS symbol period, then problematic. Problematic. If TC is less than, sorry, it is sorry, I told wrong. It is good. If TC is less than TS, it is problematic. It is problematic. Why? Because TC basically describes the how long the channel remains static. If TC is the time duration, that is for TC duration, the channel remains static. After that, channel will change. So if your signal period is greater than TC, that means the channel, the signal has to face channel change. That means it has to, it will go under fast fading. If TC is greater than TS symbol period, that means there will be no fluctuation in the channel within this period. Since the TS is less than TC, there will be a slow fading. Slow fading is not harmful. Apart from that, there's a problem in coverage area also. Okay, those who are at the cell edges, they may not get good signal strength. So these are the reasons why I told that we need some techniques where we can control the channel. And the solution, possible solutions, two possible solutions today I'm going to discuss. One is RIS, other one is UAV-assisted communications. When I'm talking about RIS is basically reconfigurable intelligent surface. It's a RIS structure. RIS, there is a meta elements are there. So if you look at here, 1, 2, 3, 4, 5, 6, 6 cross 4, 6 cross 4, it is a 6 cross 4 RIS. So these elements are made of meta surface. These are meta surface basically. What happened? It is attached with one controller. There is a FPGA controller. FPGA. It is FPGA. FPGA. That is a programmable. So what happens that signal, say any signal that it is generated from BS, it will hit to that surface. Not only is a single place, it will hit to the there and reaching to the receiver. It will hit here, reaching to the receiver. So all the elements will reflect, and like this way, all the elements will reflect the signal to a particular intended user, that is say user 1. Now, what is the function of this? This is basically passive. It does not require any RF chain. That is the biggest advantage. You can save energy. Basically, if you look at the MIMO and other antenna techniques, it needs a RF chain. Okay, RF chain, that means it needs power. Basically, if you want to run the RF chain, you have to consume power. So that where the RIS plays an important role, it does not need any RF chain. So it just reflects and towards the intended user. So you can save your power consumptions. What happens here? See, if I think about a RIS, what the RIS controller does. See, if there is a transmitter TX and there is a RX receiver. So just for a single line I'm taking, there would be, say, it is 6 cross 4. So from transmitter to the receiver, there were 24 lines, channels, and to the receiver, from reach to receiver also 24 channels. Just for understanding purpose, I'm taking only single line, say from reach to TX to reach and reach to TX. So there is an uplink, that H, say H uplink, H downlink. H uplink means mod of HU and it reverse say J theta 1. So that angle of this channel, angle is theta 1. Similarly, the downlink HD is equal to, I can write HD angle to the power of J theta 2. So its angle is theta 2. What the RIS will do, that this controller will compensate this angles theta 1 and theta 2. So it will set the elements angle. It will set the elements angle in such a way that the angle introduced in the uplink as well as the downlink, that is theta 1 and theta 2, will be nullified. So for each element, there will be phi. For each element, there will be phi. So this one, phi theta 1 plus theta 2. So theta 1 should be theta 1, it should be theta 2, it would be 0. So this phi, what would be the phase? That would be decided by this controller. Now, how it can set, that will have, let me see. Okay, fine. Now, UV rays questions are how it can set this phase. Basically, what happened before that transmission of data, the BS will send the pilot signal to the user. So it will go reflect and come back to the user one. User one is aware about this pilot signal. Then from the receive pilot signal, since it is aware of that, so obviously the receive pilot will be distorted or changed. From there, it will extract the channel information, that is called CSI, channel state information. Extract the channel state information and it will feedback to the BS. What BS will do? BS will inform to the controller about this link conditions. Accordingly, the RIS controller will set its phase phi, and automatically phase means this phi I'm talking about single element. If I take for all this element, there may be phi is equal to, I can write say phi 1, phi 2, and like this up to phi 24, since there are 24 elements. So it will sit in such a way that the reflected beam will be directed towards a particular user one. This is how it is working. So if we look at the key features, large number of passive reflecting elements, programmable phase controller, low power consumptions, no active RF chains. These are the advantage key features of this RIS. Now, how RIS help in wireless? Obviously, it will there is a signal reflection. So direct the signal towards the user in the blocked region. See, this that direct link is already blocked. So that's what it will. The direct signal cannot be sent to the user one. So RIS will direct the beam to the user one. Okay, improve the SNR. How? Because it is direct the beam towards the particular user. So obviously, the received SNR will improve. You can use as an extension. So if I say want to get extend this, so I can put another RIS here. So this would be say extension. This signal should be here, go here. Then some user to this one. So I can extend the average coverage also. Since the energy consumption is low, so that's what it is energy efficient. Now I'll talk about little bit how this phase RIS elements means. Basically, I'm talking about, say this is your RIS, and these are the elements. These are the elements. I'm talking about these elements. How that is how we can describe analytically that reflected signal, because this is the incident signal EI and this is your reflected signal ER. How I can mathematically describe? ER is equal to tau into e to the power j phi EI. EI is the incident signal, ER is the reflected signal, tau is the reflection coefficient, and phi is the angle introduced at this particular element, which I described previously by phi 1 for element 1. It may be phi 2 for the element. Normally, these elements are made up of, that is RT, some substrate is there, RT durate. These are the metamateria. Okay, some examples are given. RT durate 58806002. What are the features of this? Features such as low dielectric loss, stable dielectric constant, and good performance at gigahertz frequencies also. So if you look at the particular this RT durate 5800, this dielectric constant is 2.2, and that is tangent loss is 0. These are all material properties. When it is designed, these are required. So for this will taken care of by Professor Jogesh Kumar Chaukikar when you will deliver the lecture. That time you will tell. If we look at the structure, normally one by one, first is copper patch, then substrate that is hydrogen, then ground plane, then tuning component, then bias network. So these are the basically these are different parts of this RIS. Now I'll talk about UV assisted communications. It is in case of UV assisted communication, unmanned vehicle are placed and at a, placed in a placed in such a position that it can provide a line of sight. See, if that the one scenario is given where the base station wants to serve these two users, but they are obstructed by these trees. So UVs are placed in such a way that signal is going to the UV and then directly it is delivering to the users U1 and U2. So that wherever see you cannot deploy say cable or some base station at the sea areas or some mountain area regions. If you want to deploy network here, then in such situations, UPs are very good, useful. Even in the disaster scenarios, say earthquake happened or some flood is there, that your conventional network is completely destroyed. In that case, if you want to means go for rescue, you should know where the people are. So how do you can come to know? So best way you just deploy a network. You can whether you can communicate with them with some messages, or you can see that they are. You can take images from the image analysis. You can see the position of the areas. So this is how the UV take place an important role or in a vital role in communication system also. So in such networks, UAV act as a aerial base station, maybe a relay or some data collection platform for IoT that I told already. What are the advantages? It's a flexible deployment, line of sight. You can get a line of sight there. Rapidly you can deploy it, and it can give a wide coverage region. Say, here you have shown you single UAV. I can place another UAV here. I can place another UAV here. So it will send data to it. It will send data to it. It can deliver to this area. So I can extend my service region. When I club this UV and if I use the good features and of RIS and UV, means RIS plus UV assisted communication, then it would perform well and it would obviously better than a separate RIS assisted network or UV assisted network. Okay, that a certain situation is given here. Here you see this is see how you can use. You can use RIS separately. See, normally, if I think that ship is moving and the ships are moving, but I have to deliver some message, since they are moving, if I think about a fixed receivers, okay, fine. A transmitter is fixed, TX is fixed, receiver RX1 and RX2 is fixed. I can find the optimal position of the RIS, where I should place the RIS to get the optimal service or optimal quality of service. But once this user starts movement, then what would happen? That optimal position will change every time, every instant. So which is if I placed it fixed in a fixed manner, then it won't be feasible. Means not that much perform well. Uh, Perform well. Better how I can make the placement of this flexible. So better you deploy the rigs at in UAV. As the users are receiver users or there is a relative motion between transmitter and receiver, automatically for that instant receives find its optimal positions and place itself to strengthen the quality of or give strength to better what should I say, that the receiver can receive best highest SNR, means good quality of service. The other way we can use it here, the where I talked about trees only, but When I'm talking about RIS plus UAV, means both are involved in the communication system. Previously, what I talked, there only RIS was involved, but UAV placing the position of RIS at optimal positions. But when I'm talking about UAV plus RIS, that means basically both are involved in the communication process also. Means not only this RIS is reflecting the signal, as well as the UAV also processing the signal and send to the users, get informations to the users also. So this is RIS plus UAV. So what are the benefits? So obviously they give signals, improved signal coverage, the enhanced signal strength in non line of sight environment, reduced path loss, flexible and adaptive wireless network you can deploy. Okay, you can, it becomes more flexible. Now, so I already discussed about given introductions about RIS. First, I told what a why RIS. Then I talked about RIS briefly. Then I talked about UV. Now I'll little more elaborative way. I'll talk about RIS with a system model. Take two scenarios, scenario one and scenario two. In case of scenario one, I'll take considered that transmitter is a single antenna as well as the receiver as a single antenna system, where RIS has in number of elements. This is one element, two element, three element, like in number of elements it has, and this is a RIS controller. Okay, now how I can model the uplink channel? See, since it's a single transmitter, already I mentioned there will be one link, because once it is omnidirectional. So obviously once the information is radiated, automatically it will hit to each element. So that means it will create independent links. So if there are n number of elements and there is a one antenna, so the number of channels will be created n cross 1, which is shown here. HTR1, I can say this is HTR1, this is HTR2, this is HTR, say L, and this may be the HTRN. Okay, so it is a n cross 1 matrix. Similarly, I can get n number of links from RIS to the receiver, and that matrix, since it is a 1 and n, it should be 1 cross n. So that's what it is written, HRR, RIS to receiver 1, RIS to receiver 2, HRR n. So these are the vectors basically. So now we come to know the channel between transmitter to the RIS and RIS to the receiver. There, what about the phases? Phases I can define, because already I mentioned each element there will be one phases. So that's what it is. Since there are n elements, so for each first element there is a phase is phi 1, for element 2 phi 2, for element n phi n. So it is a n cross n matrix. It is a n cross n matrix. N number of elements, so n cross n matrix is basically we used to write as a diagonal. So since the diagonals are non-zero elements, so now if I try to model what would be the end-to-end channel, so can I write? I can write a end-to-end channel, each end-to-end channel, that means from here to here. If I want to write, that is HTR, means that is a transmitter to the RIS, HTR. Then there will be one that phi, and reflection coefficient is also there, into that is a R2R. This would be the end-to-end channel. If I take the direct link also, then this HD will be added. So that's what, if you look at here, if X signal is transmitted, so YDL, that is a, this is called DL. Okay, HD, HRR, that phi, that is a basically angle, HTR into X plus this noise. So this can be written as this way HD, because here each link basically link to link. Say what is described here basically. Both way you can represent. Both way you can represent. Say this is 1, 2, 3. So I'm writing this and this TX, and this is RX. So say this is HTR1, HRR1. Then this HTR2, HRR2. Then this HTR3, HRR3. Say. So basically, if you look at X is transmitted. So from this first element, second element, and third element. Just I'm taking 3 elements. So I can write X into HTR1 into tau1, this reflection angle, into theta1 plus X in just a minute. I do HRR, I forgot, HRR1 plus X into HTR2 tau2 theta2 HRR2 plus X into HTR3 tau3 theta3 HRR3. So now if I this add them up, I'll get this type of equation. X should be common to all. This HRRN, because it is multiplied, so this should become HRRN, n is equal to 1, 2, 3. HTRN is there, and this is the basically phase profile. It will capture these effects. So I can write the expressions, that is a received signal this way also. This is the so TX2 RX, and if I write RX to reverse direction, means when the signal is going from TX to the RX direction, this direction. But if I write, this is called downlink. If I write this way, there is an uplink directions from receiver to the transmitter. Then I have to write the equation. Just see here. Just I have to use the transpose. Be careful when you are, whether it is an uplink or downlink. If you said uplink, means receiver to the transmitter to transmission, okay, then you have to use transpose of this. So I can summarize this one. So RIS to TX to RIS channel is n plus 1. RIS to RX is 1 cross n. RIS phase matrix is n cross n channels. And end-to-end channel, that is effective end-to-end channel, is HD plus HRR 5 TR1. Now, this is a single antenna case. If I take both transmitter and receiver as a multiple antenna, means transmitter TX as multiple antenna, and RX also has a multiple antenna. RIS is there. What would happen? See, previously, when I'm thinking about this scenario, the RIS to receiver direction is a passive beam. Basically, there are two types of beam. One is active and passive. RIS to RIS is directing the beam towards, beam is basically from RIS to receiver. Because RIS elements are setting their elements angle in such a way that incident signal form a beam and reaching to a particular user. So there is a beam forming at the reach to receiver end. This is the passive beam forming. But when I use a multiple antenna system, I can generate this beam this side as well as this side. So this is called active beam, and this is called passive beam. So in that case, since it is a say there are T number of antennas I used, there I used R number of antennas as a transmitter, and this is N number of elements. So obviously that this link, that how many links would be there? N cross T. So that's what, if you look at this HTR, that is this side is basically capital HTR. From transmitter to the RIS HTR, it is a N cross T matrix, N cross T matrix. Whereas if you look at this side, RIS to receiver side, it's a N and R, so it is a R cross N matrix. So that's what this RIS to receiver link you can find R cross N number of. It is a matrix size R cross N. So direct link, obviously direct link, since it is a, what about the direct connection? It has T number of channel, T number of antennas, it has R number of antennas. So obviously the direct link, the direct link dimension would be R cross T. So it is, that's what it is given in R into NT, a direct link. What about the phi? Phi is like same. So what would be the effective channel? This is the effective channel, the same as it is. Here they are written both because they are vector data, vector. So if we summarize, HRR, R cross NR cross N, phi N cross N, transmitted to the RIS, it is a N cross NT, and an effective basically end-to-end channel basic dimension is NR cross NT. So if you look at here, that uplink is uplink N cross T, downlink N cross, sorry, R cross N. Okay. Now, if we look at here, if phases are perfectly aligned, basically how the beam is formed. If we, what is the advantage? This each block, what I told, they will set the phase in such a way that that entire signal that be directed towards the direction. Means what happens? This signal path, this signal, anyone, just randomly you take all signal paths, they, when they reach to the receiver, they are aligned in the same phase. If they are perfectly aligned, means if they are all are positive or all are negative, they will be added. Or if they are reaches a different phase, someone are positive, someone are negative, then there will be a destructive effect. So that's what it is. If the phases are perfectly aligned, that channel gain would be proportional to n square. So one question, just put a one question, say PT transmit power is PT is equal to 1 from a transmitter to a receiver. This is RIS. And n is equal to say 4. Say P is equal to beta I say 0.1 milliwatt. What about the receive power? PR. PR would be always HEFF square into PT. So if I do it here, so it should be 4 square into 0.1 milliwatt. That means 16 into 0.1. That means 1.6 milliwatt to receive. Now the question is, you may raise that we have transmitted 1 milliwatt, but at the receiver, when I checked, I received 1.6 milliwatt, which is violating the energy conservation rule. How it is possible? It is not possible. Here is some modification is needed in the concept. I have transmitted PT 0.1 milliwatt. When it is transmitted from here, it would face path loss. So when it reaches to the RIS elements, it may not be the same 0.1. Say for an example, it may be 0.01. For an example, it will lose its power since it is traveling distance. So if I take uniformly that all the that incident that all the elements receiving that same 0.001 milliwatt, in that case, if you calculate what would be the receive power, so it is 16 into 0.001, it may around 0.016 milliwatt, which is less than the transmitted power. This is physically it happens. So theoretically, I can say that scales with n square. Anyway, so how we can model the SNR? So if X is transmitted, so that average power, that E of expectation of X square is equal to, I can write PT, and receive signal power, that I can write PT into mod of HF square, and obviously that receive signal power is this one, and noise power, noise variance is sigma n square. So this is my SNR model. Once I come to know the SNR, easily I can model what is the outage. What is outage? The probability P out. P outage means what is the probability that your received SNR falls below a targeted SNR. That is called outage. I can find out this one. I can find out what is the link capacity. If this SNR is instantaneous, I can find out the instantaneous link capacity. If this is the average SNR, I can get the average link capacity. Say for an example, this is instantaneous. In that case, I'll get instantaneous link capacity, that is B log 2 1 plus gamma I. In that case, I have to averaging this one with respect to the fading. That is what is the distribution of gamma. So C average I have to find out, that is integration of 0 to infinity C of I f of gamma I into d of gamma. So this is how I can find the average capacity, that is also called ergodic capacity. So these are the different performance parameters. From once you come to know the link capacity, you can easily find out what will be the throughput of the system. That is equal to the time duration frame time into that capacity. C average. You can find out what will be the throughput. Now I'll take quickly two works already that we have done. Here you see that the work one that we have studied, transmitter access point, there is one RIS, two users are there, DR1, DR2. That directly, there is no direct link, heavily blockaged. They are basically using that cellular user links, though they are secondary users, but they are using the cellular link. So obviously, when the cellular user is present, they will transmit in underlay scenario. Underlay scenario means they have to transmit the control power, and when the cellular user is using their channel, that is already told you underlay scenario. When they are not using the channel, then they will transmit in overlay scenario. That means with a sufficient power transmission, because the cellular users are not there. The primary aim here, do not disturb the cellular user, because channels are there only. So when we modeled it, we got that received SNR model, this one for DR1, received SNR for DR2, this one, and that capacity of the link for CR user 1, that is denoted by CDR1, capacity for DR2, CDR2. Then we found the outage 1 and outage 2, then throughput for user 1, throughput for user 2. This is for all for overlay scenario. Overlay scenario means cellular users are not using their channels. In case of underlay, we observed that gamma DR means underlay means C user is there, C users using their channels for their transmission. So obviously that DT user has to transmit with a controlled power. That's what you can use that PO. What would be the PE optimized power? What would be the optimized power user 2? We have found, and accordingly we have modeled that SNR for user 1 and user 2, and thereafter we use find for hybrid mode, means if the user cellular users using, then automatically the DTT users they will move to the underlay mode. Once the cellular users absent from the channel, then and there they will move to the hybrid mode, overlay mode. That is combined, I can say, a hybrid mode of operations. If I do, we got this throughput for user 1, throughput for user 2, and there is the total throughput. What you observed, if we look at here, without RIS, that black blue line, once I use, and the user, this is just this to check for user 1. So that black circuit, that is marked by black circle, this is without RIS case for DR user 1, and red circle for with RIS. So I think that using RIS, the outage is reducing. Same you can get for the same you can find for the user 2 also. This is because once you use the channel gain improves. If the gain improves, that means receive signal strength will improve. Obviously, the SNR improve, outage will reduce. We investigated for different RIS elements. You can find if the number of RIS elements for a given SNR, if the number of RIS element increases, automatically the performance of each user will improves. Here you investigate the throughput. As the sensing time increases, there is an optimal throughput. Thereafter, if the sensing time increases further, the optimal throughput decreases. That means you have to keep your sensing time that much, or okay, because after that, if you increase the sensing time, automatically transmission time will reduce, your throughput will reduce. Here, all three network, underlay, overlay, and hybrid are investigated. Hybrid is performing better. Next, I'll talk about, because next work I included NOMA. NOMA technique, basically non-orthogonal multiple access technique. Here, what happened? No, that power is not power is allocated to the users according to the channel condition. See, there are three users: user 1, user 2, user 3. If the link condition is bad, then it will be allocated higher power. If the link condition is good, it will be allocated low power. So if you see here, that power allocation green, then orange, then this one. Now how they extract the signal? First, user 1, it will detect its own signal, fine. For user 2, it will detect user 1 signal first, then it will subtract from the, say, again repeating, say S1 for user 1, S2 for user 2, S3 for user 3 is transmitted. User 1 directly detects its own signal first. User 2, what will do? This composite signal is received by all three users. This composite means X is equal to this one. This X is received by all three. What the user 2 will do, it will first decode S1 and subtract from the composite signal. This is one written here. Then it decodes its own signal. In case of user 3, it will detect first user 1 signal, subtract. Then user 2 signal, subtract, then its own signal. This is how it is works NOMA. Same we implemented for multiple RIS conditions, multiple RIS we have used. I'm not going to these equations. Here we found that see these two results you see, perfect and imperfect SIC. If it is a perfect SIC, then outage is low. If it is a imperfect, outage is high. SIC means cyclic. This what I discussed in NOMA. This is cyclic interference cancellation. For user 2, if we think user 2, the signal is S2, but S1 is an interference, S2 is an interference. So for user 3, S3 is the signal, S1 and S2 are the interferences. If they cancelled perfectly, then I can say perfect SIC. If they are not cancelled perfectly, means at least some interference remains, then I have to say it's an imperfect cancellations. So in practice, it is always imperfect cancellations. So imperfect cancellations always gives you higher outage. You can observe. Thereafter, since I told discuss NOMA, that one result is given with NOMA, without NOMA. So without NOMA, if you see, without RIS and NOMA, if you see, this is the throughput. RIS NOMA, when I combine them, the throughput is increased significantly for given sensing type. Next, I will talk about UAV-assisted communication. Already I told what is UAV-assisted communications. So again, just consider a wireless scenario, single antenna. Just a system model is there. If you think about UAV here, there is one transmitter, one receiver. So it's a uplink, downlink. So this is HU, HD. If I say both can be modeled using this link channel equation, where this portion is basically link attenuation, you can say. D is the distance between TX and RX. How you can find D? DIJ, it is written here. You say it has some coordinates, say X, I, YI, and it has some coordinates XU, UV, YU, and it has some height at it. Height is also. From there, I can easily find out what will be the D between transmitter to the UAV to the RIS. So using this equation and this basically e to the power minus j 2 pi by lambda, this is basically phase shift during the propagation. Due to the propagation for distance traversing Dij. Okay, so this is how we can model the UAV channel for UAV assisted communication. So there are two type of links are there. One is transmitter to UAV, that is HTU, UAV to receiver, that is HUR. So that effective channel. So see, this UAV can act as a base station, can act as a relay, whatever it is. It can, if you think about a relay, just relaying the signal, that means there is some relaying techniques are there. Amplified forward means it will accept the signal and amplified and forward it. Another one is a decode forward is there, means it will receive the signal, decode it and forward it. Okay, so obviously here there is some gain, that G gain is there. Just cross the lines. Just still cross the gain. Okay, G is the gain. The signal received at UAV, I can write Y is equal to HTU into X. X is the transmitted signal plus NU. NU is the noise. UV, obviously, after receiving the signal, it will, this is called first stop transmission. This transmission of this called first stop transmission. It will receive, then it will forward the information to the receiver. That is during second stop transmission. So this is first stop transmission. UV to UV relay transmission, that it will, yes, amplified forward I used here. So some gain would be there. So that's so whatever the received signal YU, that will be multiplied with the gain G, then it will be forwarded. So now the signal becomes XU. At the receiver, the received signal is, there is receiver link into that XU plus NI. So this would be the received signal. So this is how we can model receive signal at the receiver. Once I come to know, then I can easily find out what would be the SNR at the receiver. So receive signal power by noise power. So it is the SNR for the PT into that is a end-to-end link. This is UR, that is uplink channel from transmitter to the UAV, and this is transmitter to the this one, and this is UAV to the receiver. There, okay. Then G is there, so mod of square by this is noise added at the UAV, and this is noise added at the receiver. This can be modeled as this way. Simply way, this sigma square basically it will represent the total noise. This is one way of modeling the noise. That is SNR. This is another way. Means you find first what would be the gamma uplink, gamma downlink. Means you just find what is the receive listener here. Find the receive listener. Receive listener here means gamma u. Receive listener at Rx means gamma r. Then since it is amplified forward, then I can model it this way. Gamma is equal to gamma tu into gamma ur by gamma tu plus gamma ur plus 1. This is another way I can represent. Now we have taken a simple model. That work is done by M. Hua. It was published. That is a throughput maximization of UAV enabled wireless power transfer in a relay system, 2017. In conference, it is a very good paper. Where see the UAV is here. This is the source and this is the destination. This is the basically frame of the transmission in first half, second half. In first half, that first it will harvest energy from the source. Then source to UV act as a relay, source to relay information transmission. So there is a power split. That power splitting ratio is total power is P. Total power is for this harvesting and transmission. Total power is P. That is splitted. Rho of P portion is used. Rho times of P is used for the harvesting purpose. 1 minus rho of P times of P is used for the signal to relay. That is a UV transmission purpose. Rest during the second half of transmission. This is the first half of transmission. This is the first half of transmission. This is first half of transmission. During the second half of transmission, that the relay to UAV to destination, there is the information time transmission. So here two parameters are there. One is rho, power allocation factor, rho, and time allocation factor, that is alpha. Okay. If you look at the result, you can find for first of all, as the alpha increases, throughput increases, then throughput automatically decreases. That means there is an optimal value of alpha. Means that is a power time allocation factor. For that time allocation, alpha is deciding how much time will be given for first of transmission and how much would be given for second of transmission. That alpha will decide. So it is observed. For each case, there is an optimal value of alpha for which the throughput is maximum. And if you look at the rho value, if you find that as the rho, that is a power allocation factor increases from 0.2 to 0.4, then 0.6, 0.8, throughput automatically increases for each alpha value. This work is our work. It has been published in ITV Transaction Aerospace in 2024. This is UAV RIS. This is basically both are there. Both are communicating. This is a combination work. RIS as well as the UAV. So RIS UAV RIS enabled NOMA network for disaster management with hardware requirements. Here you can see what we found, that with RIS and without RIS, that if you look at the performance, that with RIS performance, that system outage is higher in case of without RIS. When there is no RIS, we are not using RIS with the UAVs, only UAVs serving the disaster region. Then when we placed RIU or then what happened? We found that outage is degrading. There is a black line. So obviously, RIS with UAV always better instead of single that with only RIS or only UAV case. Okay, that's all from my end. Any question? Any question? Any question? Okay. If you have any question, you can place the question in chat box. We will reply. Thank you. Bhaskar, are you there?
Yes, sir. I'm here, sir.
Could you share your PPT? Just tell me how that AI is performing there for disaster.
Yes, sir.
Just give
Yes,
a
sir.
just okay. I'll just share the PPT. I'm just stop sharing. You
Okay.
just share your PPT. So at least they can get some idea about how that they can use machine learning in placing UAV in some uh, disturbing environment or disaster situation.
So is the screen is visible, sir?
Not coming. Now it is coming. Make it full screen.
So now it is visible, sir?
Yeah, it is visible.
Yeah. Shall I start, sir?
Yeah.
Okay, sir. Good evening to everyone. Today we are going to see about UAV assisted communication under dust environments. Okay, under using DQ networks, which is an reinforcement learning technique. So initially, UAV has been for used for line of sight to challenge the ground obstructions. So the dust environment will affect the whole path. So how it has been overcome by these challenging atmospheric conditions. So, so here you can see, yeah, here you can see the UAV placed in the dust environment and these dust particles, and you can see the transmitter and you can see the receiver, and the feeding coefficients is H1 and H2. So the device transmitter has been assigned and device receiver is also assigned. UAV is also has been assigned. Then the distance has been from device transmitter to UAV and UAV to device receiver is fixed. Then the path loss for the UAV obstructions is also assigned. The line of sight and non-line of sight has been discovered. Then dust attenuation formula has been discovered here. These are all dust attenuation coefficients with Mia coefficients filled with real and imaginary dust particles. Then the received signal from UAV to from device transmitter to UAV is expressed here with the noise signal.
Where it is, your slide is not changing, Bhaskar.
Sir, it is
Go
changing,
to
sir.
the next slide. It is not coming. You wait to the equation number what?
Equation number 7, sir.
No, not showing. It is you are in the still first slide.
Is it visible, sir, now?
No, still not. You close it, then I can share.
Okay. Is it visible, sir?
No. Now it is visible.
Yes.
Change your slide. Change your slide.
Now, sir?
No. You directly go to the slide 2. You directly go to the slide 2.
Yes, sir.
First, and then result. Tell you about your little bit about your algorithm, then go to the result directly.
Yes, sir. Sir, now it is visible, sir?
No. I can see your. No, not that. Only the slide I can see. All the slides are showing no.
Yes, sir. Just a minute, sir. Now it is visible, sir?
Not coming.
Yes, sir.
This you tell about this and tell you the network about block diagram RL process, then go to the result directly.
Students, see here, we have considered the dust environment along with the UAV environment. So the agent acts with the input layer. So we have considered the reinforcement learning process. So inside the input process, there will be two hidden layers. From the hidden layers, it will traverse to output. So that will be the reward. Okay. From that reward, the actions will send some signals to the environment. Okay.
Basically, the aim is to optimize the position of the RIS. Am I right?
Yes, sir.
Providing the maximization is SNR maximization, end-to-end SNR.
Yes, sir. But here we used only UAV, sir. No, we didn't use RIS here. So we are
Okay,
fixing the
fine.
optimal position of UAV by using the DQN agent. So we are initializing the input parameters like device transmitter, device receiver, and dust parameters like real and imaginary dust parameters, then velocity, everything. Urban parameters like building height, spatial, and line of sight and non-line of sight. Then output is to fix the UAV optimal position in a 3D by maximizing the end-to-end SNR. So first we are initializing this, then we are configuring the dust parameters, then initializing the DQN agent with episodes 1 to n. Then we are resetting the environment. After that, the Q learning agent will start to update the Q function. Then the reinforcement algorithm is update to the optimal position of UAV. Then the Q learning agent will take some actions with respect to the state elements. Then according to that, the direction will move either positive or in negative. Then we will evaluate the SNR for UAV and the SNR for the device receiver. Then end-to-end SNR will be
What it
evaluated.
means movement means what it means basically positive means either it will be up, down, left or right.
Sir, it
Right?
will be all directions, sir. Three directions also. X, Y, Z. Three directions also it will act. The action will be implemented. Then the transitions will stored in buffer space. After storing in the buffer space, the target will be set to maximize the reward, and the reward will be maximized by setting the Q function. So after we getting the reward, the updated optimal UAV position, we are going to maximize the SNR and we will get the throughput. So here represented as throughput equal to bandwidth into log 2 of 1 plus end-to-end SNR of maximization. So B is the transmission bandwidth. So here are the results and discussions. So one is with UAV with dust environment and another is UAV without dust. So UAV with the dust environment we get 65, 50, meter with a height of 50 meter, and here we get 100, 50 with a height of 50 meter. So here you can see the parameter and its value. DT were fixed and DR were fixed. We got the optimal position with respect to dust environment. So 65, 50, 50. And noise variance is 1. Ground visibility is 1 to 10 kilometer we have considered. Line of sight and non-line of sight. Then probability, bandwidth, carrier frequency and transmit power we have considered. So here you can see the SNR versus throughput with respect to dust particle. As dust particle increases, throughput gets
Size of dust particle.
yes sir, or dust particle sir, dust particle radius. Order.
Size.
Yes, sir. So as the dust particle radius increases, throughput decreases. As well as you can see the ground visibility in kilometer. We have adjusted the real and imaginary values of dust particles according to the some certain dust particles like fine silt dust, clay dust, and silicate dust. And clay dust will be in industrial mines representations, and certain dusters has been also represented. So here the throughput for Leo's fine silt dust is low, and for quartz type dust is also in medium. So the network throughput will increases as ground visibility ranges increases. So at 5 kilometer, we have observed that Leo's dust the throughput has 43 4,31,337 bits per second, whereas in quartz dust the throughput is 4,71,898 bits per second. So generally in the UAV assisted communication with the dust environment has been investigated. So a DKN based oral based environment is considered for the dust channel environment, and we have found out the optimal position of UAV within a dynamic environment, and throughput has been maximized and impacted with the visibility and dust particle radiuses. So with increasing visibility range along with throughput, it decreases with increasing dust particle radius. In industrial users, we can see wherever the desert regions or industrial areas, these applications will be. And the future work we can maintain with RIS. We can mount with RIS with UAV. We can either make RIS as also communication path, or we can make just with the RIS to use the UAV as to fix the optimal position, and we can find the impact of the outage throughput or energy efficiency like this.
Okay. Thank you.
Yes.
Also, we got the idea about how to use RIS and UAV and what kind of performance matrices we can investigate or study. That how to use machine learning in UAV assisted or RIS assisted or UAV assisted communication. That this lecture gives some ideas, I hope. Thank you all. If you have any questions, you can put your queries in your message box, chat box. Uh, do you have any query right now? No. We'll reply. Thank you. Thank you. Bhaskar, close that screens. You share, close the screen. Bhaskar.